Okay. Hello everyone. Welcome everyone to Digital Futures live session. It's me, Ahmed Hassab from Digital Futures Riyadh Committee. I am a lecture assistant at the American University in Cairo and senior architect based in Egypt. It's my honor to moderate today's session. I'm so excited. This session is joined by Digital Futures Young Committee and the organizers, Anil. And I would like to mention next week we have the third session on robotic fabrication. We'll be waiting for you all. Today's session is the second about robotic fabrication. We have a very interesting panel of speakers joining us from different places through our open call. We have received very fascinating collection of projects. Today is my lucky day. I'm honored to be with these amazing instructors. Let's start our presentations. This will be our first session out of 5 presentations. Our presentation is streamed on YouTube and Bilibili. We'll be waiting for reflections, comments, and questions. Our first presenter will be Alexander from MIT UC Berkeley.
Thank you. Very happy to be here. Looking forward to hearing all of your thoughts and comments. I will screen share.
Thank you.
Okay, so my name is Sandy Kurth. I am a new PhD student in the computation group at MIT. And before that, I was working at UC Berkeley with emerging objects, getting my Master's of Architecture. So most of my work focuses around 3 things: leveraging local material with cheap and flexible tools to make digital fabrication technologies more accessible. And recently, this has been all about big mud. So for the next 15 minutes or so, we'll run through my journey to big mud in the last few years. This all began with a printer I built some years ago, just for fun, to print clay. I think many of us began getting into digital fabrication in a similar way. And I loved printing outside with this creation. Got into some digital fabrication on my own, trying to sell pottery that was 3D printed, and then realized I wanted to scale up and do real research. So while at UC Berkeley, I primarily worked with emerging objects. I'm sure many of you are familiar with these projects, the 3D printed cabin, Hakal Digital, which is a wattle and daub, mud and plastic printed structure, and some other various small projects. So I'll just cover a couple of those today. Of course, team is very important, and I will reference these folks throughout in the next few minutes. They're all great contributors and collaborators. So a lot of this journey started with a tool that was largely developed by Barak Darwish and I called Potterware, which is essentially a web-based slicing tool for clay printing that tries to make the process very, very simple and usable for everyday users who don't have much CAD experience. And I encourage you to check this out. We just launched a new version that's pretty fun. But what does it allow you to make? All of these kind of forms and shapes that are now somewhat familiar, with texture patterns and multi-print for production, if you want to do production pottery, that kind of thing. So from there, that became a great tool for exploring how to engage students and getting people from different areas with different materials involved. So this project, led by Ron Real, basically took earthen material from both sides of the US-Mexico border and students from both sides of the border, and gave them printing machines and let them experiment with their local material in our tool, getting an introduction to digital fabrication. And this project was definitely an important starting point for me in this future work, as we'll see. So this is our first big first big mud print, which we did in tandem with this smaller project of getting high school students to print. And so this developed into this very large scale printing work where we were using local mud and straw to just 3D print as big as we could in different forms, begin to think about integral furniture, thinking about how to work in a relatively harsh site with limited power and, you know, uneven surfaces, which I'm very excited about. I like making the tools as kind of dumb as possible so that you can work in any position instead of just in a warehouse with a perfect concrete floor. And so this has moved into larger and larger structures. We've built some stairs, more enclosed forms from local earth. And this last summer, we spent a few months working on building an actual sort of house structure, creating linkages between different earthen domes. And for all of this work, we're using a very simple robotic arm. It's just a 3-axis SCARA type robot. So it works in polar coordinates and is very lightweight. So 2 people can carry it around and position it. To extend our reach, we made a plywood 4th-axis rail for about $60 US, which was maybe my favorite part of this last project. It just had 3 positions and allowed us to work on one structure while the other part of the structure dried in sequence. And so here you can see that these forms just kind of emerge out of their own material. So this mud we're using is literally dug from 50 feet away from the project itself, just with a tractor, and then run through a screen to get out any large gravel. Worked on some more integral furniture, experimenting with like how much you can do with tool pathing in the mud. Some integrated lintels and wooden structures as needed to create doorways. And you can see the beauty of this very sort of cheap, simple system is that you can print while it's raining and nothing too bad happens. And the machine can handle getting covered in mud and all of that sort of thing, which I think is compelling for a actual future where we use this kind of technology. So the final product looked something like this. The interior is still in process, but it's a large 3-domed structure with a space for sleeping, a space for eating, and there's actually a bath in one of these. So look for more pictures of that soon in the future. So moving on, I want to talk a little bit more about the work that I've done with students at UC Berkeley, where we're pushing on this idea of using some vernacular forms to solve some of the issues in large scale robotic printing, specifically enclosure, making roofs. You know, we see lots of these concrete boxes with the standard wooden roof on top. And that I find kind of frustrating because we have ways to make compression only roofs. So we explored the idea of squinch vaults and interlocking toolpath patterns to get better adhesion between layers so that the whole system can work in compression as it's being fabricated. And we'll be publishing this work pretty soon. So as we worked on this, we began trying to scale up this squinch vault technique. We got to about a 1 to 10 scale before COVID hit and shut down our fabrication efforts, but these are kind of fun little videos of just the early process. Printing at an angle. And this proved to be relatively successful. Now I'm working on some of the some structural analysis tools to make this a little bit more robust so we can scale to the next level. Yeah. And so I'm actually going to just leave it there with those couple of projects, and thank you all, and encourage you to reach out if you have more very specific questions about methods and things like that. I'm happy to talk about them anytime. You can reach me at Kurth@MIT here. And I look forward to seeing what everyone else has to say about their robotic fabrication processes. Thank you so much.
Wow, this is very interesting. For me, I'm working on the same research about using clay and so on. We'll have a lot of discussions at the end.
Yeah, we'll have to talk. Thank you. Yeah, that was just a couple of projects. I didn't want to go into too much.
Yes. Okay, let's move for the next presenter, and we'll be waiting for your discussions, reflections, questions, and so on YouTube, Bilibili, and Discord. Our next presenter will be Sajai Kumarji from IAC. Yeah, please introduce yourself and then start.
Hi everyone. Firstly, thank you for having me on this presentation. It's a great opportunity for me to be here. So I'm Sajai Kumarji. I'm an architect and a robotic fabrication consultant based out of Mumbai, India. And I'm here presenting one of my projects, which I did it in my Masters of Robotics and Advanced Fabrication at IAC. So this was a very interesting project for us because it deals with concrete 3D printing, and it is an area that has been something that I've been working with for quite some time. So without much ado, I'll just start to share my screen. One second. So this is a project that was developed by me and my colleague Omar Gennady under the supervision of our directors Alexander Debord and Aldo Salazzo at IAC as a semester project in the Masters of Robotics and Advanced Construction. But it generated so much interest that it became more than a project for us, and it became an academic submission to Digital Concrete 2020 conference. And so we are very excited to show our work and kind of discuss about the kind of possibilities of 3D printing and how 3D concrete printing brings into the construction world. So, I mean, we are all excited about concrete 3D printing. I mean, it has been promised. There is a lot of promise this technology brings into the field of construction. And there is a lot of hope pinned on to how this is going to transform the entire construction sector. So that is one area which generates a lot of interest within the subject. Now, over time, over a period of around 20 years, let's say, we have developed quite a bit of technology into addressing certain factors within the 3D printing industry, where we have worked with the setup, we've worked with the mixes, and we've also we've also gotten a lot of performance in terms of tackling the compressive forces. But one area of research which still has a lot of promise is the ability to develop tensile forces within a 3D printed framework of using concrete. So this is where we entered, and this is where we tried to engage into our project. So trying to address the tensile forces or the flexural strength within concrete while 3D printing is not a new subject. I mean, a lot of parallel research is happening across all institutes, and there are various strategies that people bring out. And within this huge domain of knowledge, we want to focus our research into a small area where we're trying to print, where we're trying to embed reinforcement simultaneously while printing. Whereas there are numerous strategies that involve post-printing, pre-printing, and with numerous other materials. We are focusing our research on using discrete reinforcement, which is printed simultaneously, which is embedded simultaneously during the print process. So this was the abstract that we kind of developed into an academic submission for the digital concrete conference, where what we tried to do was embed discrete U-shaped filaments in the shape of a staple, which could be embedded within the layers and could interlock to create some sort of tensile forces which can be tackled, which can be beneficial for our to tackle tensile forces. So going about our research methodology, we kind of divided the whole process into two stages, where one so that we could work on it parallelly. The first step was to evaluate the concept as to see whether this process works. And the other step was to see how to develop the robotic fabrication. So two parallel methodologies were devised so that so that we could come across with a universal solution, perhaps to see whether this strategy works and if it can be mounted onto the robot, and we can develop an autonomous method to tackle the 3D printing, the reinforcement problem. So how do we go about to evaluate the concept? One of the areas is to see how to conduct tests to see how it performs under load conditions. So we all know that concrete doesn't have too much tensile stresses and it immediately cracks, whereas steel has steel yields because of its ductile nature. So based on that principle, we decided to add about a point load onto our printed elements to see how it performs. And so this was a test that we devised to run to see whether our reinforcement strategy would work. So if you look at the image on the right, where we see between the area where the concrete fails and where the steel yields, anywhere within that range, if we were to manage the failure of our printed segment, then we could consider that there has been some amount of tensile stresses can be tackled at a certain degree within the printed element. So based on that, we started with our test to see how our concept works and how we can develop this concept. So we had two control samples. One was completely unreinforced, and one had a regular continuous reinforcement along the base. This was supposed to be devised as a beam sample. And as for the test samples, we had a kind of a staple-based reinforcement at the bottom. And one sample, we kind of overloaded the whole reinforcement by having reinforcement at the bottom as well as on the top. And so for all tests, we required a framework of how to go about the testing process. So we had a setup based on the kind of mixes that we use, the kind of staple sizes that we use, and the amount of force that we applied onto the reinforced segment to see how it performs under stress and to see if tensile forces are actually generated by the use of this technique. So yes, so we made a few samples and then we applied some a point load onto the center of it, spanned it across two ends, and to see at what are the failure points. At what point does the whole sample fails? So we came up with some interesting results. I mean, so the first result was the lower base end, and the second result of the continuous reinforcement was the ideal benchmark that we had. And when we saw how our tests, how our samples tested against it, we found some increase in tensile force, in the sample's ability to tackle tensile stresses. But it's not nearly enough for it to be a valid reinforcement technique. And that we understood very easily, because the amount of increase in the tensile stresses is near negligible. And at this stage, this does not stand. But we were able to identify the reasons as to why the amount of tensile stresses generated were kind of so little. And we came about developing a sort of guidelines which could in effect increase the amount of tensile stresses generated. One was to increase the horizontal length so that the effective overlap of each reinforcement staple was greater. Because once we evaluated the point of breakage of the beam sample, we saw that a lot of these failures happened due to insufficient overlap and due to insufficient length. And the other thing that we needed to check was the viscosity of the mixture as well, and to see what other problems that may face, that it may have caused during the curing time. So once we had a vague idea that this concept could be refined to into a valid method. So we went about doing the tool which has to be mounted onto the robot to help print the concrete and the staple concrete. The first attempt was to devise a custom staple tool, which we very soon realized is a bigger task. It's a bigger project by itself. So we decided to go for a small hack where we decided to adopt an existing staple gun, an electrical carpenter's staple gun, decided to modify it to force it to staple into the printed layers, and it can be mounted onto the robot as such. So this was an initial estimate of initial design of how we wanted the tool to be, where we had the concrete nozzle, which was trailed by the staple gun. So once the nozzle prints, the staple gun immediately staples beyond it, which would, again, the staples would embed into the layers, thus adding the kind of tensile reinforcement into the concrete. So this was our setup that we came up with. And based on that, we decided to start off with a few tests. The initial tests were we tried to test manually to see how the concrete works, how the material reacts to the stapling. And as you can see, these were done manually to see how it performs, to test physically if there were some problems with the whole technique that we're using. Our second test involves got a little more refined when we started to use the staple gun and start to adjust the pressure required to embed these staples sufficiently deep into the concrete elements. Finally, we took it upon to mount it onto the robot, and see how the trailing effect happens. But as you can see in some of the images, you see that it's not the most efficient thing, because we came to know because the difference between the stapling nozzle and the layers were quite substantial, which we had to rectify at once it became normalized. So the final setup was to automate the whole process, to have the robot print and staple simultaneously at the same time. And so this was the fourth setup that we used, where we define all the layers and all the positions of the staple reinforcement were identified. And once that was identified, the key areas, and it was basically optimized, and a toolpath was generated. Even developing the toolpath, we needed to ensure that both the nozzles traveled along the same line, so that, and there was no offset, which would result in mainly the trailing nozzle, that is the staple nozzle, not following the lead concrete nozzle. So this was a more refined experiment, where we had a better control of the layers, we had better control of the reinforcement, and we were able to simulate the whole thing within the robotic, the rapid code that was generated. And as tests kept increasing, we realized that while training was efficient, it wasn't the most effective, this thing. So we decided to rotate the staple nozzle, so that once a single layer was printed, the whole tool was rotated 90 degrees to allow for the stapling nozzle to happen immediately after that. So at every pass, we had two passes, where once it would print, and then along the second pass, it would staple the entire reinforcement within the embedded system. So this was a kind of an image of how we envision it. The first print happens, and the second stage, the whole reinforcement is stapled into that. And based on that, we got on to a few more samples to test how overlapping happens. So there were a couple of problems that we needed to debug to ensure that there was no obstruction created due to improper embedding of the reinforcement, because the next layer would affect the next layer, and then the whole print would be ruined. So to ensure that all the reinforcement was embedded properly was very key to understanding how effectively the printing happens. So some of the images. And to ensure that some of the tests happen, we try to test it on clay as well, to see how the reinforcement, how best we can control the reinforcement, and what are the most effective strategies, how to print between layers, and how to overlap the reinforcement. And having the second setup, where you don't where the staple gun doesn't trail the extruder, allowed for us to create that interesting overlaps, as you can see in the image out here. which wouldn't have been possible if it was purely trading the extruder. So this is a video of our testing that we conducted. So as you can see here, because of the height difference between the nozzle, the staple nozzle, the embedding of the reinforcement doesn't happen as effectively, which we rectified in the later tests and prints. So these were some of the problems that we identified early on in our tests and the prototyping, so that we could rectify in the subsequent tests. So this is to ensure that once the stapling is done, the next layer passes on to it without too much obstruction, thereby still ensuring the print quality was good enough and there wasn't any obstruction in the prints that happened subsequently. So this was the second setup that we did, where we just initially printed and okay, so once that was achieved, we saw what was the possibility, how to automate the whole process from the design to the final printing. And we thought of using a couple of machine learning strategies to see if we could develop a fully design to print workflow where the whole process was done within the software. So we used a couple of machine learning algorithms, particularly in this case, the k-means clustering, which was actually fed in data of positions, the moments, the deflection data. And based on that, we were assigning weights to the states which required reinforcement. And that was then used to develop the reinforcement print path. So we started out with analyzing the geometry, doing a couple of finite element analysis onto it to understand the bending moments, to understand the displacement within the geometry. Once that was identified, we broke down the geometry into various states, and using the k-means clustering algorithm technique, we divided it into states. And based on the weights that were assigned, we developed a reinforcement strategy which was then, this reinforcement strategy was then finally fed into the robot, so that the whole reinforcement, so that the whole design was printed without autonomously. So based on that, once that was achieved, we tested. We have a few future steps about how we want to go about it. First was to try different tests and refine our reinforcement strategies, understand the kind of bond strength, do a pull-out test. So a couple of future strategies are under the works about how we want to take this project forward to develop into a more viable reinforcement printing strategy for concrete. And and so this was, this was a small sort of a vision for how we would love to see this project developed onto an in situ fabrication technology setting. So yeah, that was our project, and thank you for giving us the opportunity to present our project. Yes.
Yeah, thank you. That was very interesting. I have a lot of questions, but
Okay.
let's move
I
to the
gladly answer anything, all
presentation.
the questions
Yes,
that you have.
and
Yeah.
then we'll discuss. Yes. um, okay. So our next presenter is Samim Mehdizadeh from DDU-TU Darmstadt.
Hello.
Yes,
Okay, I'll
hello.
share the screen.
Yes, introduce yourself and then start your presentation.
So hello, my name is Samim. I am a research fellow and PhD candidate at the Darmstadt Digital Design Unit, led by Professor Desman. And today I will give a briefly introduction about what we are doing in the digital design units, and also going more to the details what I'm doing during my PhD. So this is our lab. These are our two robots, Fred and Ginger, the friendly robots. And we are working on the digital procedures for the design and the robotic fabrication. And this is always not that clean. In these moments, the lab is getting messy with the more material inside. And this is the moment that I like, because the digital is transformed to the physical and the matter is flowing to the materiality. So I'll go to give a briefly introduction about what we are doing with the robots in the general. And one of our strong focuses is on the co-robotics and on the human-machine collaboration. And this is one of the early prototypes in 2016 at the Smart Geometry in Chalmers University, Gothenburg, in Sweden, which you can see we are focusing on the same procedures by additive manufacturing, but not putting the layers on top of each other, but adding the discrete cubes and also getting the support modules out of them, which are not glued. And this idea has been flowed by more to the focus on the geometry of each module, each discrete element, and trying to make assembly sequences for the different modules. And as you can see, the robots can assembling the parts on top of each other, but how far, if you're going to that by the autonomous driving, has been researched in this procedure with the robots, is going to be the decision maker, and our researchers are the laborers for the robots by feeding them the material. As you can see, the visionary sensor is leading the autonomous driving of the robots by knowing exact placement of the modules. And we have worked on that in this procedure. Basically, my colleague, Bastian Vibranek, has worked on that, and to showing and proving that the robots need more sensors than the camera and visionary sensors by getting a better understanding of their building environments during these small failures. And that had led to the project, which is called the tactile sensor and the tactile assembly, that the robot is now reinforced by the tactile sensor and can see the compressions of forces of, for instance, this box on the top, and these tools can be added on that. And the result of that has been proved in the exhibition by the Lights Biennale at the Frankfurt am Main, the closest city to our university. As you can see in the video, the robots can sense the modules by the compression on the head and the end effector, and can seamlessly have a better understanding of the environment and how to put in the materials and its path. So these ideas has been developed by what we are calling it the human-robot collaborative environments. By this idea, by this project, as you see in the right side of my screen, the human are placing some parts, and the robots can have a sense on that, can have making a design decision, and trying to collaborate with the human for the fabrication procedure. Which these ideas has been projected to the more complex materialities, and this is my one of my first interesting moments, getting a better understanding on the left side of the screen. As you see, get a better understanding with the hyperelastic membranes and how can we articulating them by adding the materials to that. In the part of the presentation, I'm going to focus on the Rotiform, a procedure that I am focusing on and have developed during my PhD at the Digital Design Unit. And we are focusing on the computational design, the robotic fabrication, fabric formwork, and innovative concretes. Mark Wigley conceived the moment that our planet is empty of the humans, and someday maybe aliens are coming to our planet. The only evidence that show that our species have lived on this planet is the concrete. So this is the most material that we have built with that. But on the other hand, the concrete, due to the guardians, is the most destructive material on our planet. So there's a lot of place for the improvements of how we are building with the concretes and how we are utilizing this material. And on the other hand, the architects are conceiving the material concrete as a fluid stone in this term that we are designing something beautifully. We are making a formwork and pouring concrete inside. And specifically, the moments that we are using the fabric formworks, this is not what we are going to get out of this, and this is what is going to happen, unfortunately. So the hydrostatic pressures had led us to work on this procedure, which we're calling it Rotiform. And one of the interesting projects that I'm going to show is the P-wall by Andrew Cutlass, which shows how he utilized the hyperelastic pressure and how he utilized the digital tools to exactly getting the material behavior in the way that he is expecting it. In this project, the deformation of the fabric formwork is emerged by the hyperelastic pressures, and all of a sudden this beautiful wall is happening. So we are investing on the membranes, sort of the fabric formwork, the hyperelastic membranes, to utilizing them and using them as a formwork for the concrete. In this project, I've used latex balloons, as you all may know, at your birthdays. And by stretching the points and the anchors out of that, all these individual modules out of the concrete can get form activated by the minimal surfaces. And to avoiding the hydrostatic pressures, we are using the procedure which is called rotomolding, is a conventional procedure in the industry, and by rotating the formwork, we can distribute the material even on the surface of the formwork, which is showing that the hydrostatic pressures are not there anymore, but we are using the kinetics to distributing the material over the surface of the formwork. The whole procedure is going to this chart by the physical modeling to the computational design frameworks, which are using the grasshopper and kangaroo, and that allows us to bring the whole procedure to the precision. This has been proved by our installation at the AAG conference 2018 at the Sweden, and further on we have developed the different modules out of that by looking through this procedure and trying to interpreting it as a driver to designing the building elements, which you can see there are beams, there are ceiling panels, which have been designed and materialized by our students at the Digital Design Unit, the combinatorial systems, and these discrete elements, which has been powered by the software Grasshopper plugin developed at the DDU WASP by Andrea Rossi, one of our colleagues at the Digital Design Units, and the combinatorial designs has been also tested during this procedure. And as you can see, more than half of the tests are going to be a failure, but some of them can work, and we are working on the procedure to bring it in the different dimensions. Out of the whole design studios, this diagram is one of the moments that I'm particularly interested in, that shows that how are different procedures and different systems in the design has been leaded to this procedure and enables to the emergence of the different systems. And at the end, the whole exhibition of our students has shown that there are different possibilities to materialize by this procedure. Further on, the design studios had led to more explorations on the spatial qualities and what they can be meant for the architectural space, which I'm not going to focus on that in this small talk, but how we are going to bridging the gap between the robotic fabrication and concrete. Basically, in my opinion, there are like two different procedures that we are focusing on. One of them is that, as we have seen in the last presentations, 3D printing by putting the layers of the materials on that, which is showing a lot of room for the development, the question of the reinforcement, as we have saw in the last presentation, and also limitation by adding the material, the quality of the surface. But on the right side of my screen, you can see the robotics concrete has been a lot in this direction of CNC milling and subtracting the formwork and pouring the material, which is also a wasteful procedure. We try to bridge these two the different dimensions of the research and these two different research fields by Rotiform, which is also utilizing the formworks, the fabric formwork, and also adding the layers of the material sequentially inside of each module. And what we are really got inspired by is a project has been done by Graham Kohler at ETH Zurich, called Smart Dynamic Casting. It shows that the kinetics and the robotic path has become the driver of the form and driver of the design. The kinetics has been simulated in this project, and this simulation has been used to show us how can we equally and eventually distribute the material or uneventually distribute the material over the surface of our formwork. Based on that, different machinery setups has been developed based on the size and proportions of our elements, and also the robotic path had been developed for this distribution of the material. As you can see in this video that we have tried with the bottle of Coca-Cola, which doesn't put us in that side of the world, but we have tried to distribute the material and try to have the better understanding of the relation between the material distribution and the robotic path. Another way that we have used the integration of the robotics is the collaborative robotic assembly of adaptive false work, which shows that the robots had shown us where should we put these thread rods and get a mark on the latex balloon and stretching them to get the exact form as we want, as you see in the right side of my slides. And the other test has been done with the HoloLens AR, HoloLens glasses to show us how can we get more assistance of the digital tools for exact placements of our adaptive false works. On this side of the project, we have looked to how far we can scale our procedure and basically focused on the funded research project. We have focused on to scaling up this procedure for materializing 6-meter long columns, and also what we're calling it free sequential casting, as you see on the left side, and different robotic setups has been developed for this project. As one of the early prototypes, we have started to prototype and materialize approximately 1 meter 20 centimeter long, and by using the different digital tools as 3D scanning, we can have better understanding of the deviation of these thin sheets of the hyperelastic membranes. So this side of the project is also on the development, but what is also getting the project interesting is the question of the reinforcement. And on the collaboration with the fiber at the Stuttgart, we are trying to making the multi-material system between the Rotiform and fiber placements, and trying to improve the seamless robotic procedure. As you can see, the material side of the materiality side of the project is now focusing on to bringing the concrete in the way that is getting cured under motion, and also have a good covering on the fibers. And one of the early prototypes that has been developed by the robotic larger scale robots is showing that there is a lot of room for the exploration on the robotic path and distribution of the material over the formwork. One of the interesting aspects that I'm focusing on is that how can we bring in super complex way of the distribution of the material so that we can replace our labor work from our students by the robotics. So these geometries are getting that complex that uneven distribution on this framework, on these formworks, is getting more complex and complex. And this is a small project. The focus is that how the humans can teach the robots to following their perception of the material distribution and trying to follow them. And the robotic path is generated based on the human behavior. As you can see in this video, the robots are trying to do what the humans had shown them after by connecting the physical environment to the digital environment and bring it back again to the physical environment. Thanks a lot for watching my presentation, and we will be really happy for any contact, for any visit on our website, and any contacts are these the governors of our boards, Instagram and Facebook.
Yes, thanks a lot. I have too many questions for you. I think I need 2 days to ask you my questions, actually. Okay, but that was very interesting. Thank you. I'll ask you at the end, but I prefer to ask you one question at the end. How do you imagine the future? Or how do you imagine the digital futures? You went through a lot of scenarios, so I prefer answering this question. Okay. Saving time. Yeah, let's move for the next presentation. Our next presenter will be Ryan Burati from Technion. Okay.
Hello, everybody. Thank you for the opportunity to present here and the opportunity to leave my house after 1 month in quarantine. I had a special permit to come to the Technion. Just 1 second. So let's start. My name is Ryan Burati. I'm a master's student and a researcher at the MTRL laboratory at the Technion in Israel. And my research named the architectural scale rotational casting, and my supervisors are Professor Aaron Sprecher, Professor Yasha Groveman, and Professor Arnon Petu. I want to start with a brief overview of the topic that occupied me in the recent years. As you can see in the left graph, there has been a sharp increase in the pollutant emissions in the world in the recent years, and it can be seen there is a direct link between the pollution and the global cement consumption. As Samim talked about also, we have some On the other side, you can see the productivity in the industry in general, and especially in manufacturing. Productivity in construction not only didn't increase in relative to the general industry, but even has declined. The decline in construction productivity can have many causes. However, the direct impact on the considerable effort is needed to develop custom-made construction products. Therefore, one of the main advantages of the fourth industrial revolution has been called the automation, or in our case, the ability to design complex architectural systems without producing them effectively, making them non-feasible. My research deals with the development of construction technology that the main objective is to overcome the gap that I described. I'm involved with the development and production of hollow construction elements, and as you can see, a glimpse on the day in our laboratory looks like. Rotational casting is an existing method that involves produce hollow elements with complex geometries made out of polymers. Mainly used with liquid polymers. This method utilizes biaxial rotational to generate centrifugal forces and disperse the material in the mold until it hardens. Rotational casting is highly efficient to producing lightweight plastic objects. However, it's not commonly used with inorganic cement. This is due to long hardening time and poor workability of conventional cement mixture in comparison to liquid polymers. Within this domain, the research focuses on employing the rotational casting using inorganic cement, allowing to produce lightweight, hollow concrete architectural scale elements. This research focuses on a custom robotic system capable of producing mass-customized hollow complex elements. The robotic system facilitates the production of a catalog of architectural elements which vary in size, shape, weight, and structural performance. In this presentation, I will present the experiments performed with cementous mixtures customized for rotational castings aimed to achieve uniform thickness within the cast elements. It then provides a framework to assess the applicability of this manufacturing method in architecture. The assessment focuses on designing a customized robotic rotational casting process and optimizing the fabrication parameters. The study began when I was exposed to this concrete in the Construction Institute research lab while we were experimenting with different material. This specific concrete has a high workability and adhesion characteristics in initial strength and fast hardening time. After that, I was looking for a way to utilize these parameters, and after a manual experiment, we decided that there is the feasibility to using this material for the method that I mentioned. If you said in the video, the whole process takes around 10 minutes. It's really special for this concrete. There were many failures along the way, but already here we noticed that the potential for further development. What do I mean by potential? Going back to my initial review, between 30 to 60% of construction costs today are the processes by which produce the molds. Moreover, the molds end up being discarded in one point or another. Of course, we are not mechanical engineers, but why won't we try anyway to make this prototype of this complex machine? I'm sorry. So, we tried to produce the prototype by manual rotational machine as part of my final undergraduate project from 2 years ago. I proposed to build a pavilion to the entrance of a department our department in the Technion. And after 3 months without sleep, endless malfunctions and broken parts, we produced about 8 elements and decided to hang up our gloves and start over. But we had the feasibility, we had the elements. For comparison, this hollow structural element with average thickness of 10 millimeters and it weighs around 7 kilograms. In comparison to a conventional casting, it would be weighed 5 times more. Another concept that contributed to the further development of the potential of the production of complex curved surfaces with stretched textile without using CNC milled molds. So then I started my research at my master's at the MTRL lab. And with this starting point, we developed the second prototype according to our requirements and also work on simulation for casting process development and different mixtures. We are currently completing the first stages with the aim of producing a standard for the production method using this flexiglass cube, as you saw. We are examining the machine variables in relation to the concrete mixture behavior, and then we will compare the early age and the mature properties of the casted elements in the purpose to find the optimal characteristic we want for the mixtures. I have some picture of the different failures that we had, as you can see. You can see the difference between the mixtures also. And I just wanted to share the last thing we did last month before the quarantine. We almost finished the initial steps for these standard cubes that you saw, and we started to examine how we are going to change and examine the different textile that we wanted to use. You can see here, this casted element was a 3 millimeter thickness of 3 millimeters, and the whole process of casting took about 7 minutes. And thank you very much for listening, and I hope my English was good enough to understand me. Thank you.
Yeah. Thanks, Ryan, for the presentation. That was very interesting. Okay, let's move for the next presenter, Yuan Wei Di from CETA. Yeah, would you like to introduce yourself shortly and then start your presentation?
Is everyone see my screen now?
Yes.
Okay. So thanks for having me and giving this opportunity to present my work. And really enjoyed everyone's project. I'm a research assistant at CETA and joined the Fungal Architecture Group. Today I'm presenting my previous work, stitching bar on textile design plus fabrication. This project is part of my master's thesis developed in 2019 at University of Stuttgart in IT master program, supervised by Professor Menkes and Professor Jan Knippers, advised by Maria Yabina, Martin Avlanze. And this project had a lot of influence after I'm joining the CETA. To give you a really neat idea of this stitching part, to develop a parallel design plus fabrication process and focus on the textile manufacturing by the investigate bespoke robotic and AR design tools for shaping woven textile divided in space. And so it's very long. So conducting by the two main contexts, textile architecture of manufacturing technique and bespoke robotic in the context of mobile robotic fabrication. Starting with the textile is widely used at a variety of the scales, ranging from clothing to architecture. Recently, the growing availability of manufacturing has been influential in digital design at all scales. A propagation of the traditional textile techniques and the use of the soft material have created a new possibility for design methods. And even more, we see some of the project use bespoke robotic to carry material in order to making the space that become more size specific. Here's getting a lot of project, like 30 project from building made by textile or use textile technique in the fabrication. And the current state of these projects definitely will see the most closing to the offsite rather than have the onsite. Namely, it's most of the cases are fabricated in factory. Compared to another material like timber has more comprehensive manufacturing ecology. Also look at the graph, knitting are taking a lot more in the customized and in terms of material efficiency, and the whiting seems can do more homogeneous from ranging from on-site or either to off-site. But here I want to highlight is the joint methods. It still relied on the really manually sewing. So here's the project emerging from. So borrow the existing workflow from the bespoke tailoring. It helps to identify where the new strategy could adapt in order to utilize on the bigger scale. And here's like the three moments I found really interesting is the designer need to take out the fabric from the model in order to fit into the machine or either cutting and drawing. So my hypothesis is, could we leave all the fabric and all the fabrication will stick on the model, a seamless institute design and fabrication. The main three area, in the project will carry on the textile institute design strategy and customized stitching robot and for on-textile drawing method and AR design assistant for real-time design and robot control. Focus on the logic of the sewing sequence when performance in 3D by mobile machine, then locomote along material itself in order to design and fabricate simultaneously like a tailored design developed on the model. The design assistant has to be able to control the custom robot and allow the user to sketch in 3D in the AR environment. In order to explore the proposed morphology of the joint textile in 3D without need to flatten them, the mobile sewing robot was developed. Just take a picture of a robot and how it operates, and you just need to attach on the fabric, and we can start stitching and sewing. Yeah, and the proposal for the design plus application is providing a comprehensive 3D workflow by stitching bar and AR design tools. Firstly, sketching and arranging the space by the textile. And once you temporarily fasten the textile together by the pins, from the initial place, then you can put it into the next stage, attach to the robot and start stitching. While the robot is working, the designer can simultaneously design the next steps. Designer could experience the space quality in the real time while the forming the textile is happening. The textile design strategy is using a single continuous row textile to extrude the geometry. In the process, the robot extends on its own environment. Because the 3D spiral pattern it becomes more problematic for the normal sewing machine. So these three models will be examined later in architecture scale in common demonstration. In the hardware, the robot body using a two body strategy is separated the sewing machine into needle and the hook. A stitching bar achieves a higher freedom than the conventional sewing machine. Here is a criterion of the development, like the comment on non-tension fabric, also the weight distribution. Second, that the tension control and the needle precision. The last part will be communication and system control. Here's the older iteration from the 0 to 4, and the final version is 7.448. It's a funny name. And there's the whole iteration of this project, except the needle and the rotary who are from the shell. The rest of the part you can 3D print. In the wheel development is try to solve how to climb on the loose textile and alignment of the needle and the hooks. Another parameter is equal weight distribution between two bodies. In order to avoid the skewing on the textile surface, the input weight of all necessary hardware on the board is on the right. You can see all like the 3 motor, and one side is the motor and the rotary hook. And the deviation is sitting grade without the printing body part. According to the textile property, the robot weight limitation was defined max 1 kilogram. And the final version, the 7.448, the robot weight distribution as follows. The needle size is 488 gram, and the hook size is 472, resulting in the deviation of 60 gram, which is, I think, is a big challenge. It's a big success. However, they still have a limitation of the locomotion is climbing close to the edge of a different thickness. This is examined like 3 or 4 millimeters high, but it still can climb on parallel. The tolerance of a needle hook to the hook tip is in the stationary sewing machine is usually under 0.6 millimeter. And alignment tolerance of the problem is resolved by the wheel design in the stitching part. And the final tolerance is approximately 1 millimeter. In the conventional sewing machine, the press foods prevent the fabric being pulling up and keep it flattened when the thread is interlacing. Back to the robot, the typical 301 class lock stitch require the consistent tension on both sides of the sewing machine. And the hook side is controlled from the bobbin hood, and needle side was controlled by the lever arm and the needle bar position. And so the last problem was the tension control. The stitch bar have the customized lever arm to minimize the size. Lever arm will put in the thread while the needle is leaving on the fabric to the highest point. Then lattice is made by 5 pieces, which you can see from here. The horizontal lever arm will moving. So that's the only reason we use a really complex gear set to design this. And the sewing protocol, the motor position value was taken into account in every iteration of the control routine. If you frame the needle breakage, the experiment to evaluate the vertical surface with curved seam and using offline control, this experiment, the robot could stitch vertically and horizontally, and also circular seam, but it seems able to keep the consistencies of orientation and the stitching radius. So the semi-manual control from the designer in the real time allowed to adjust the robot deviation as well as making the design decision on fly. In order to prevent the mobile device ecosystem, the design system is created primarily in the Swift language on iOS platform. In the software development provided user interface for the controller robot, and furthermore, it could be extended to the robot team for later application. These 3 parameters are the needle loading point, the wheel traveling time, the wheel velocity, and the comment side will provide the UI interface and how we treat the parameters. The first is a manual control interface. Just scrolling the number, designer will know how to control robot and can observe the test of behavior. And the second part was the pattern interface. You can take in the manual control further to design the robot behavior. It provide a seamless pattern editor for the designer and can be operated without supervising. And jumping to the AR, by moving the device and the screen, you can draw you can sketch in the AR environment. And technically, this AR environment could share to any iOS device, which is you can use your iPhone or using your iPad. And the idea to using the same platform to engage robot control and the modeling in AR. So without sending the data to somewhere, which is you don't need to send back to the Rhino or any cloud service. In order to doing that, is optimize the sketch being directly on the iPhone is really crucial. Finally, we can start demonstrating, and these are all the ingredients you need. In the demonstration 1 is try to prove the spiral pattern method through a stitching bar and manual control interface. Also testing the minimum radius of the surface curvature is set the diameter is 60 centimeter, 2 times the robot body, 4 times, sorry. Then in the result of the demonstration is proving the spiral method could be done by the mobile robot and prove the design plus fabrication can happen in parallel, which you see the video. When the robot starts stitching, I can continue to do the design. Because the swing is a reversal joint method, so all the fabric can be used later on my second demonstration. Yeah, and the demonstration 2 was further explore of the spiral strategy by folding the edge in order to control the overall curvature of the resulting geometry, and also testing the AR sketching ability on the test style. But the primary goal of this demonstration was increase the layer stitching from 2 layer to 4 layer. The conclusion of the experiment was the 4-layer equal like 4 millimeter is become a problematic for the robot because the pressure, the soft press foot kind of against the body. Also, maybe the needle is kind of having some kind of issue, but overall, I still can able to sew the whole sew the whole geometry. And so in the end, we see the Taylor derived working on the body. It's a very productive process, and now we can treat architecture as a body design in it, on it, and also collaborate with our material responding immediately to its behavior. And yeah, thanks for your listening, and I'm looking for the further discussion.
Thanks you for your presentation. That was a piece from the future. Thanks so much. There is much to think about. I can see the possible futures through these presentations. That was fascinating and very interesting. I have a lot of questions, and I can see on our Discord channel, our committee members had dozens of questions. So anyone would like to start, or I can?
Ahmed, can I start?
Yes.
I wanted to say, first of all, these were really great presentations. You know, and you actually, Ahmed, you said this, the digital future. And too often, frankly, I've seen people kind of reinventing the wheel and doing things that have been done 15 years ago by people like Barocos Neves, and thinking they're doing something new. They're not. They're just simply kind of replicating, reinventing the wheel. But today I saw something really, really innovative, and I thought all the presentations were great. I just wanted to, I want to maybe pick up on Sujay. I mean, from a personal perspective, I collaborated with Barocos Neves on a bunch of projects. We also worked on a project for NASA for a 3D printer for the moon and Mars. But I actually met Beroc through IAC. He was giving a lecture there, 2009, I think, and Marta Malay was invited him. She's no longer at IAC, but anyway. But what was interesting about today's presentation, the staples that you were using are actually kind of similar to the cleats that he was thinking of, but your notion of using the staple gun I thought was super inventive and really interesting. The one thing that I think that I think you need to push further was the kind of let's say the tectonic logic of what you're building, just to go and replicate a kind of standard kind of, I don't know what it was, a kind of Byzantine arch kind of thing, doesn't necessarily make sense. And one of the things that Marta did, and this is back in 2010 as well, but when she was teaching also at the AADRL, they did a series of explorations to see how layered concrete, how the geometry of the form itself could actually lend itself towards a new kind of structural logic. But using the layered technique to make sure that you didn't need scaffolding, you didn't need any support in any way. And there were some really inventive forms coming out of that. And I would just simply say, I think that's the next step for you guys to really explore that. So it's a combination of both the geometry of the form itself that's going to give it certain structural strength, but also a kind of layered technique that allows you to print without scaffolding. And from that point of view, I thought that the Sandy's work that he was doing, the kind of parabolic form, I just want to say something to Sandy too. So I don't know if you're aware of that, but there was a project that Beroc and Madhu Fangavello and myself and some others did for NASA, which was exactly that parabolic kind of form that you were showing, which I thought that was kind of interesting in itself. And I'm just one thing I have is I'm interested in knowing how far you push that sort of parabolic logic, because we were thinking that's the way you can print without scaffolding and get a form to work. And I know that, for example, Shajé Bouchian has been really exploring the possibility of 3D printing and producing the most extraordinary forms without any support. So I just wanted to ask Sandy to say a little bit more about that project and where were the failures and how far do you think you could push that logic? Because I thought that was really, really inventive.
Thanks, Neil. Yeah, I'm very aware of the Kashnevis work, and I of course admire everything you guys have done there. I would be super curious if any of that was actually ever like printed, because what we've found is that a lot of the Kashnevis stuff, it's like, wow, this is so cool, and then you're like, wait a second, how do you actually, like, what happens when you do it? And so, as you can see, the kind of approach at Berkeley is largely, we spend most of the time you would normally spend on analysis printing, right? And now I'm very interested in making much more robust models and modes of analysis for that. I mean, what we found is at the 1 to 10 scale, printing a vault in earth, so they weren't not even concrete, like the stuff takes days to dry. You can make a vault that is that span is the same as its height pretty easily if you know what you're doing with the material. And you can do that at a scale that is maybe the biggest one we made was maybe like almost a meter wide. And then we had COVID, so we couldn't. We were really going to do the full scale, but I'm hoping to be able to work on that very soon. But in terms of the structural logic, yeah, I mean, it's basically people in Egypt and Iran have built this way for hundreds and hundreds of years with earthen bricks, and basically anywhere in the world where there is a not a great supply of timber, masons and builders find very ingenious ways to build without formwork. You just don't actually need it if you're smart enough about the structural design. And so it was interesting, like basically the process of the design was just mimicking as closely as we could some of those structures and understanding that, you know, the way a like Nubian vault, as they're sometimes called, works is you have to have an S-bar wall, right? That's much stronger than the rest. So you calibrate your tool pathing so that you create a thicker back. So I haven't gone into too much detail. We're working on a paper on this, but like the thickness of the vault varies quite extensively based on that patterning to account for loading and to create as supportive a structure as possible. So the wall thickness in the most recent tests varies quite a lot to achieve that. And that's something I'm kind of excited about and hoping to scale up. And I'd love to try it in concrete too, if anyone is interested.
Yeah, just to follow up on that, I mean, that sounds really interesting work. I'd love to see the kind of research coming out of that. Yeah, I mean, Baroque was a little too protective of his technology and maybe didn't push it far enough. What happened, of course, was Winson actually kind of copied. We introduced Baroque to the Winson guy, and he just copied it in some ways. But Baroque was flattered that actually the internal reinforcing, which Sujay also used, actually worked when they did it on site. So that was it. I think, I mean, but there was a lot of research. I mean, this is the thing I think maybe that should have come out more, that Baroque was doing a huge amount of research on not only the material you used, and he was working with a French concrete company, but also the kind of the nozzle that was used. I mean, you know, when you got a material in suspension, you compress it, it tends to squeeze out the water. So he really worked at that. So, you know, in some ways, I wish that information was more in hand for others and things. But I mean, in some ways, he was too reticent about it and too protective of his technology. I mean, I will say one thing is that I think some of the kind of fantasies that everyone had about, oh, you could fly this in for an emergency, there's an earthquake somewhere, and you could build this thing. That is complete fantasy. You know, you really, these technologies are very sensitive. You need exactly the right sort of material, and so on. So the idea that somehow this is going to be used for emergency housing or for large-scale, low-cost housing, unfortunately, is not the way that it's going to work out. But I just want to applaud all of you, because I think today was really, it was a digital future. It really was a digital future. And now I feel that kind of, you know, the future's in safe hands. You guys are exploring these things. I thought they were super inventive, all the projects. So congratulations. I'll leave it to everyone else, but I was just blown away by this. Thank you. Thank you.
Thank you.
I want to say,
I would like, just before Marina, I would like just thank Sandy for just mentioning Egypt and Iran using some traditional techniques and so on. We are having a session about Africa and traditional techniques into construction using mud and rammed earth and so on in a few weeks. Just stay tuned, wait for us. Move on, Marina.
Okay, thanks. I want to jump to this comment because I think it's very interesting what Neil is thinking, and I wanted to move it from to different point of view. That is that we are thinking about layering horizontal in a horizontal way, but we are not. Sometimes we can add this logic to a view of the vertical layers, because maybe this idea of scaffolding. I was watching, for example. And even I was thinking also in this fat sculpture, no, which is like this idea of RobotNet, and think not against, but the differentiation between the more fat structures and take the yes, surfaces that we are thinking. And maybe it can be something to be thinking that the differentiation between the internal form and the external form. I mean, that is something that the Baroque has, or had, or still having. And maybe if you, for example, the scaffolding is not just the result of the structure, and you can design the interior with a different shape than in the exterior. So in that way, the complexity can help to yes, given in to make like independent systems, and to make free form inside, and not just the result of the external shape to maintain, and to maintain the structure. So I was thinking that maybe that can be a third option, like not only you want to make a curve, so you have like this zigzag scaffolding inside. That's an option. Another option is to try not to have scaffolding, so you have like a really thin surface. And the third option can be like, okay, you have the scaffolding, but you can design the interior with more freedom. So that's just something to add to this point.
Yes. You know, I have a project nowadays in UAE, 3D printed building in concrete, 900 meters. And we have a problem of the interior texture and finishes. They are asking how the interior will be, but the answer is it will just be a 3D printing texture. We can manipulate that texture, but if we would like to add like the normal finishing we have, so where is the point of doing a 3D printing? It's still, you know, this point is still a question, because, you know, the general public, the client is still having the idea of the normal finishing, the normal spaces, but some of others stay thinking of the future. They still has a fuzzy imagination how the interior space would be, but I would like to hear the answers from our presenters. If someone have a reflection on how the interior space would be. We used to deal with the architectural element, but how the interior space would be within these digital features, proposed digital features. A lot of possible answers.
I mean, can you say, I mean, just quickly before they give the, one thing that Baroque patented was a kind of like a trowel system or a spatula that would smooth out the surface as it was printed. And I think the patent's running out soon, but yeah, it's a good question. That's a good question.
I mean, I would contribute one thing to this in that I think, even though this all feels very much like the future, we are basically like very crude users of a new mode of craft and production, right? Like I think as a community, as we begin to excel more and more, at least in the printing realm, we'll begin to discover greater modes of like beauty and formal control over things like texture, and that will become the language of these new buildings, right? Like you could smooth the inside of the building, or you can make it its own language. And I think we see that with like tiled masonry. Like no one would want to hide like a Gustavino vault. It's so beautiful. And that's because that's a very, very high end of craft that we haven't quite hit yet in this new technology.
Okay. So, Sami, you would like to...
Yes, I just wanted to address this question of the interior, and which I think that you're addressing about this, the tactile and the visual qualities of what we are building. And maybe, I mean, I personally believe on that all of these qualities are getting more interesting in the term that they're emerging out of how the procedures and the fabrication procedures are leading to that. Especially in my case, all the interiors are inside the components, which no one sees. But I think that you're mentioning the
architectural interior, the interior space inside it.
Right. I mean, maybe we are going to define some new borders on that, because you're addressing the very first impression of the users that 3D printed houses, which is going to build its own culture or its own language. I think that takes the time, because one of these interesting I think one of the interesting visions is that since when we started to adding the finishings on our surfaces in the whole history of the architecture,
Yes.
how far did it come? And because there's a lot of switches, I think that Neil Leach has also mentioned a lot in the different texts, and about this culture of the tectonics, and I personally believe that everything takes its time, but this is a good question that maybe we all going to thinking about it, about the future of these qualities or what is going to coming out of that. Though I like the surface of 3D printed concrete elements.
Yes.
Maybe I can add to this. I think it's really fascinating to see how all these research projects are basically bridging the gap between what we know as geometry and material. And I can argue that like geometry is cheap, and it's geometric representation and computation of geometry is becoming cheaper and cheaper. I mean, maybe the first and second decades of computational design, we were focusing on making this computation cheaper. But material is expensive, no matter what, right? We are trying to do, let's say, more with less material. So that's obvious. And somehow innovation in fabrication sort of sits in the middle of these two, in order to make the production of also cheap geometry, which sometimes can be complex, also cheaper. And it's really interesting to see how all these projects are trying to sort of innovate in that front. And I also want to connect to the comment of Marina, who mentioned this idea of interiority and exteriority, and how we as architects and designers try to sort of have this tendency to make clean surfaces in the exterior and sort of leave the engineering or rough side of our design hidden. So maybe there is some sort of this sort of hidden agreement among ourselves that we want to make the exterior clean. And when I look at, for instance, the two projects that they were working on this, let's say, rotary molding, these two projects that they were focusing on basically casting on a rotating mold. What was interesting to me was the fact that in one of the experiments that we, I think it was Ryan did in this boxy sort of shape, the material inside this rotary form was failed. I wonder if this is because of the logic of the geometry. Let's say, is it not complex enough to handle this complex movement? And then you move towards more complex geometry. So is there some sort of a relation between the complexity that we need in terms of geometric modeling when we are working with these production techniques, and how do you basically decide about these complex geometric features that we can have in our designs. Maybe Ryan or Samim can sort of reflect on that.
I will take the microphone. I think we use this symmetrical and simple cubes in the purpose of separating all the parameters because we are looking for the how you call it? We are looking for the optimal mixture characteristics. And but when I say characteristics, it's the adhesion to the mold. And we took the, I think the plexiglass is it's the worst material we could use because the adhesion it's really low to it. But if we are, we thought maybe if we are getting the mixture that it's going to stick to the plexiglass and give us the uniform thickness to the whole element, we will get the best parameters that we can get. And after almost 100 castings, we found these characteristics we wanted. And then we are moving, right now we are in the stage that we are moving to the complexity that I talked about in the first prototype and all this textile molds and rotoforming the textile. And here we are stick to the questions of what is the complexity, and if we are separated to, as we did with the cube, the first thing that we are going to examine it's the symmetry of the object. You know, if because we have the center of gravity that it's changed all along when we are doing the experiment, and we have the center of the rotation, and we have the relation between them. And if we are doing something asymmetrical or extremely asymmetrical, we will get different results. And as you see in the simulation with Samim, we are doing almost the same idea of doing a simulation with grasshopper and see each point on the geometry where it's going to be, what is his toolpath. But after the geometry, we are going to back to the materiality because it's really different which textile we are going to use, how the characteristic of adhesion of this material is going to be, and then we are going back to the concrete. The whole process, it's going back front and forward and checking everything again and again and again. That's the idea to finding.
Maybe before Adib before Samim adds, so we are trying to sort of extend a material to a boundary, and this boundary is sort of fixed. I mean, if you look at our own body, our nerves and our whole organs are trying to also stretch out from our almost seamless skin. So I wonder if there is a sort of a relation between this exterior geometry that we sort of decide maybe in a top-down way, or is it some sort of feedback from this process of forming to decide what sort of external let's say geometry is fitting for this kind of fabrication technique?
This is the question of what is the language of this this method, because with 3D printing it's really easy because you see the layers and you realize that it's 3D printing. But in rotoforming we have the only force that affects the geometry or the product. It's this pressure we have inside the mold. And the idea is to really control this pressure because as Samim showed you, we can get a lot of concrete balloons, and but in architecture, we don't. It's really rare to see these geometries in our built environment, in the interior environment, of course. So something that it's really was interesting for me was now we try to do thermo. How do you call it? Vacuum forming for the cast for the molds and examine how it's a great question and it's something that it's really I'm not sleeping because of it for a few weeks, but we need to find the relation between the textile and the material to the geometry and how this interior pressure affected. I think it's the simplest answer that I can give you right now.
Okay, thank you. Thanks. That contribution was interesting. I have a question for Sandy regarding the idea of mud printing and using this kind of natural sustainable materials. It is very cheap. You mentioned Hassan Fathy architecture, and his slogan was architecture for the poor. So now we are using a 3-axis robot, which is open source, everyone can reach online, and then available material, it's mud, you can find everywhere. The point is in designing in new lines and data extraction and so on, which may be available somehow in the future through some plugins and so on that may help the general public to innovate their kind of, their kind of architectural, their kind of spaces and perception of spaces, interior spaces and architecture, open spaces and social interactions and so on. We know architecture has a great impact onto community, onto perception, social interaction. In Middle East, in this kind of architecture, community used to be very active, as socially very active. I know maybe 80% from my district. I know somehow everyone in my streets, everyone in my apartment, in my building and so on. My question is, using these kind of technologies, what limitations you were facing and what potentials, more than it's a sustainable material and the 3 robotic is open source, available for everyone. Is there other potentials you see through this experiment and limitations as well?
Thanks for your question. Neil and I were just having a little side conversation about some of these potentials of scaling. And I think my observation of this as someone who has basically, working with emerging objects, they're basically an art practice. Like, I don't care much about publishing the structural analysis or the exact methods. And despite that, like the actual methods are extremely complex, right? Like this is, yes, a bunch of mud shoveled out of the ground, but like, yeah, our robots are controlled by custom software that runs from our smartphones. Like the tool pathing itself, I've integrated all kinds of tools so that, like layer height varies with slope to account for like increased contact surface between layers. Like we adjust the model based on the shrinkage of the mud, depending on like how hot a day it is, right? Like there's a lot of complexity that goes into it. But I think what's useful is to think of those things as kind of craft knowledge, right? That you should share in a like simple and straightforward way that's actually useful to the people who build with these materials, right? It's like billions of people on Earth live and work in earthen structures every day. And those people, like I guarantee you, will have more success making a building with these tools, these 3D printing tools, than like 5 structural engineers with degrees from MIT who have never shoveled mud before. Like I just, with a day of training, I'm sure people who are actual builders in this material will be far more successful than people who have technical expertise, right? And so my mission is always to make the tools useful to those people. And I don't mean just constructing in, like doing some kind of like, like white savior project building low-income housing. I mean, Earth is a sustainable material and it's used all over the world. People know where to get it. They know how to mix it. They know which local, like some places use barley straw, some places use wheat straw, some people use rice husk to make the material dry faster and better and be like crack less, right? Like all that knowledge is out there. And what's needed is like cheap enough tools and robust enough tools, right? And you can push for machine learning in this world, right? You can try to be like, oh, well, we can handle a complex site condition by making some crazy algorithm that figures everything out, right, for the people working. Or you can acknowledge that like maybe the people who will actually do this work are very skilled, and what they need is tools that work as well as other tools like tractors, right? Like when the printer is as robust and useful as the tractor, then we're just building stuff. Then it's happening, right? Then this formal and geometric freedom we've been talking about, which allows you to embed huge amounts of function with a material that is often hard to kind of manipulate into really specific geometries, right? Like with mud, when you make a really thick mud wall to make a multi-story mud building, it's like a solid mud wall, right? But with the printer, you can make voids, you can make hollow spaces, you can change the insulation properties, right? And our experience last summer that was very interesting was we were printing in a place that has a long history of earthen construction, right? We're in Colorado, and the three main people working on this were Ron Real, who's from that area and grew up making Adobe bricks to some degree with his family, and myself, who has a long background in ceramics. I've worked in tile factories, making glazes and formulating clays for production, that kind of thing. And our third team member is someone named Logman, who grew up in Sudan, also building earthen structures, but in a different style. Mm-hmm. And so most of our kind of technical work would be like in the morning, we would stand there around this bucket of mud, arguing about like whether or not the mud mix was right? We'd be like, oh no, you need more water. And I'd be like, no, like you put in too much straw. Like, what are you doing? And it wasn't really the printing at this point that was the problem. It was like this like material craft argument. And we would get the same thing. People would come by who were familiar with earthen construction, right? Because in that part of America, there's lots of earthen buildings, and they would give us crap about our mud, not about our building. And to me, that was a sign that the technology was starting to work, right? Like they could see that the building was coming to life. It was like, all right, it's happening. Like you're making 2 feet of this thing a day. It's drying. It's like making a building out of mud bricks, a similar pace. But they'd be like, I don't know. It looks like the color's a little off. It's cracking. Like, maybe you guys added the wrong kind of straw. And to me, those are the conversations that give me like hope for these processes, because now we're actually like building something, right? We're talking about it. And so I think there's some balance between that craft and then also just making tools that are good enough, right? Like you have to have really good digital tools or it just doesn't happen in the first place. But you need to like, that's like step one, right? Like that's just the baseline. And then you have to push beyond that and get into like the real issues of construction. Like, how do you work with this machine when it starts raining and it's not fully dried? Like, do you have a big enough tarp? Like I like working the technology to the point where you're in the position where you have to ask like those kinds of questions. Like, oh no, we're in a pasture full of cows and cows like to rub on things with texture. And so the cows are going to destroy like the walls of our building, right? Like that's a real problem we have with these structures.
Yes.
So I don't know, that's sort of my perspective on it. But I think from the perspective of material, like the knowledge to use local material exists all over the world and should not be a problem if you're willing to engage in like different modes of thinking about technology, like yes. Sometimes people talk about indigenous technology in a way that it's like, oh, well, it's not scientific, or it's not like, how do we translate that into a structure? And the reality is you just need to work with the technology as it is, right? Like people who have built an earth for thousands of years are extremely technically advanced in their craft, right? And you as like a engineer or whatever, just need to wrap your head around the way they do that technical work, their modes of measurement. And maybe you can translate that or write it down or make it something that can work with your systems, but you have to acknowledge from the beginning that like
Yes.
There are many modes of knowledge and none are particularly better than others. And you have to work with all of them if you really want to make it happen like on site with local material.
So I think I just
You know,
add something to that just very briefly. That is that I think the materials are really kind of crucial. And we say mud, but what do we mean by mud? And I think there were some mistakes made early on. I mean, Enrico Dini imagined 3D printing cities in Africa using sand. Well, you can't use desert sand. I mean, at least there are techniques of making it usable. So I think there's another level of interrogation where we've got to, instead of saying mud or sand, we've got to be a bit more specific about what that material is.
Yeah.
Yes.
Excuse me, everyone. I think Samim actually had a question. So,
Yes.
Samim.
Yes.
I know there's a question. I just wanted to add on what Sandy just brought it up, the complexity and the tooling, because I think that this is really interesting. Exactly that we are dealing with the different strengths, with the different complexities, as Sina also mentioned it. We have the structural complexity, we have the complexity between the relation of the geometry and the process. And I think that we are all sort of dealing with that in all of the projects that we have saw today. And I think one of the interesting things is that these procedures, the digital procedures, can shift the complexity of the materiality or the geometry to the process. For instance, what we are looking forward, and I think what Ryan is also looking forward in this rotational molding, what we are doing is that how far you can relating the geometrical proportions to the differentiated wall thickness. How far can these different motion, I mean, are you doing it like that, or are you making sometimes like that to add different material thickness somewhere that might your components or building elements might getting more compression strengths? And this is like what we are not going to specifically calculating it. We can try to making our rules or our tools have a better understanding of these rules and to bring the complexity to the process. And I think that is something for me at least is really complex. Maybe Ryan has also different understanding of this procedure that we can share, but I think this is something that we are all dealing with that. Specifically when Yuven also showed us the super complex behavior of the textile and some robot is hanging on that.
Yes.
And this also dealing with the materiality, with the rheology, with the hydrostatic pressures, and also what can your component do, or how far you can use this hollowness for the embedded functions.
Thank you, Samim. I wanted to jump in with a question. Very provocative, all the talks, but I'm seeing the overall research arc here as, you know, architecture building on this history of habitation, then going into engineering. But my question is mostly on the science. What are each one of you individually tackling as a big scientific question? Or are you in the domain of architecture and engineering? Anyone?
I can say something forward. I think I'm more to helping the science toward architecture, because as we are an engineer and designer for designing the robot, so you're designing a tool for the user, and that helping them to kind of avoid to know all the background knowledge, like a really complex model or your complex digital modeling. Then it's kind of shifting all this knowledge to become more artistic, and you can really just enjoy how to create the space, or you just experience the criteria and everything. So yeah, I think our job is more helping from the science to the beauty, or the sense of the beauty.
Yes. So
if I may,
yes.
Sorry.
Yes.
Hi, if I may add to what the previous conversations and to the current question. I mean, I completely agree with what Sandy was saying. But to answer this question, I think I would look at my role, or generally the role, as somebody who abstracts technology for it to be used in a more democratic fashion. I mean, technology can be quite intimidating at times. And when you see these new technologies coming in, and there is a sense of fear at points. But yes, we need to abstract that. We need to use the knowledge that is available in the site, in the context, the local knowledge that is available. And that can help kind of bridge the gap between what technology we have and the kind of the local knowledge we have. And together we might come up with a new language which will work, probably find a new architectural solution or a space within the architectural or engineering domain. So, yeah.
Yes. Thank
Oh,
you.
just one follow-up. It seems as though that I think Sandy was very provocative in what he spoke about being on site, but this applies to everyone. You know, in the sciences, what makes it so powerful is that they're building on centuries of knowledge, and especially now the acceleration of technology, they build on each other so clearly that you can see jumps of thought. So my question to you is, are you guys thinking about this as a democratic open source type of proposition where it's open to a scientific investigation or inquiry? Or is it a kind of a hybrid model of academic and professional inquiry where you want to, you know, inspire future academics, but basically black box it so that you can build industries on it? Please comment.
I would share a comment on this. Oh, go ahead.
Sorry, please. Okay. I think Neil had raised an important point regarding this in his previous comments about how Baroque's work. I mean, he had done extensive research, but a lot of it is not available, or not. A lot of it is not has not been taken forward in the right direction. Some of them has been probably black box, and this is something that I see exclusively, not necessarily exclusively, in the 3D printing industry at least. Everybody has come up with their own strategies, and they've kind of contained that knowledge amongst themselves as an attempt to kind of commodify it or try to make it into an industry. So I'm not sure whether that is the right way when this is a new technology and we can do a lot of, there is a lot more possibilities that this technology can offer once it is kind of the base knowledge is at least shared. So I think somewhere in the middle where it needs to be a more collaborative, more research, a kind of collaborative industry between collaborative area between research and the industry should happen, where we can kind of build on to one another to create a more robust system which can help tackle some of these problems in architecture and construction.
I would follow on that sentiment and say that I think especially in this world of digital fabrication or robotics, architecture is very behind science and is just beginning to catch up in terms of understanding why like rigorous peer-reviewed research is actually important and transferable. But I think because architecture has always existed in this space of industry, right? Like architects' livelihood is dependent on actually building the thing, right? Unless they're a historian or something like that. And so I think it's certainly in my own work, I find it very challenging because, like others have said, like 3D printing people, they think every idea they have is some novel, brilliant thing, when in reality, it's like, no, if you simplified the tool, like the Potterware tool, for instance, we made, like, you know, a 10-year-old kid can now make something that 5 years ago would have been like, oh, magic, you know. And it's like, it's not that complicated. It's just that people are carrying over some of this architectural sentiment of like the brilliant artist or the, you know, like the genius individual creator, when in reality, like what science teaches us is that, like, no, everything takes hundreds of people working really hard, and no project is a single brilliant mind, or it's extremely rare in our modern times. And almost all of it references and builds on a body of knowledge that is not fully acknowledged or recognized in the literature, right? And so the challenge that I find as I'm now trying to translate some of this work into a more academic or research focused context is like, how do I properly cite like cultures of building and material practice that have not documented their work in this kind of way that industrialized engineering does, right? Like I want to acknowledge whoever first came up with these like vaulting techniques that I'm copying, right? But I don't know their name, right? Like we can talk about Hassan Fatih, but he was basically just one of those people who inserted himself through written work into the body of knowledge. So now everyone references him, right? But like there are others, right? There's just people making. And so for me, it's a huge question in architecture and in other sciences, like how do you actually share and use your work in a way that is not just stepping on the knowledge of others and not acknowledging like a real history of that knowledge? That's a question.
I have a point. As you know, my grandfather's house is made from mud, okay, and it is built by his father. It is more than 150 years old, and it is two-story building. You know, with our technologies nowadays, if you are going to build a building made of mud with two-story building, that would be very complicated and may collapse. I believe the point is, this is very, very interesting point, how the community is thinking and what the community is doing, and how we architects think that we are doing or exploring, investigating, whatever, how we express that word. We usually think of inventing the wheel, but not developing what is existing, what potentials we already have in our communities. We used to start from the beginning and then achieve the same as the others has achieved, and so on. But I believe we need to do, to have the end from someone, the end research, and then move forward beyond this and so on. We need to share more. This takes me to a question. The question is, the perception, how the community, how we can work on the community, general public perception of what we are doing, their perception on the technologies we are using, and its reflection on their lives. I believe we need to study more what is already exist and what we are doing, how this can be integrated somehow, and how it can be. The point is, if the community didn't recognize what we are doing, if they don't understand what we are doing, so what is the benefit from doing that? The community must feel what we are doing, must be able to recognize, and so they can request our services. They can request using this kind of technology.
Maybe I can extend what Ahmad is saying about perception, and also maybe built on top of what Gustavo mentioned, in the way we are sort of positioning ourselves in the discipline and industry. Are we doing science or are we doing architecture? And I want to refer to one term that almost all of the presenters were referring to, and that was a speculation. So in many of the presentation, we saw that maybe in Sergey presentation towards the end, you said, okay, this is a speculation about potential application of this, or in Samim presentation, we saw some speculations by students try to get this really focused, maybe scientific sort of research, and think about a master plan, right? I'm sure that some of us won't like this term, but we as architects try to sort of envision a larger picture, and in that larger picture, we sometimes consider community, we sometimes consider the entrepreneurial sort of dimension that our work has. So with this in mind, I want to point out to some of the presenters. Maybe I would like to hear from G. How do you see the technology that you're developing can be scaled up? How can you scale it up, and how can you sort of envision and think of some architectural applications? But I think this question is sort of open to also other presenters.
Let me think about it. But I think so. The robot I made is sort of a kind of argument that how we can extend our technology to be more mobile, but we keep this idea. So think about it, because for example, the Tesla building, now we see it more and more, like maybe fiber winding or either from the ETH, they have this kind of a neat candela. But think about that using these industrial robots. If you were doing a renovation or just maintenance, you are using the same setup, like really heavy industrial process to just make a single column for the agency. So back to the answer was, okay, these technology actually is helping for the people which don't know how to use in robot, or you don't know how to mix in the clay or using the soil or you're using the material. As an architect or architectural research, we should looking forward to well document our research and share our knowledge to be more science, because they are actually document all the property and just publish onto any conference, and people will just learn from this knowledge. Because so far like, in the human history, we're using the textile, concrete, timber, and to build everything. But why we keep the secret? Why we keep the everything in the material property as a secret? Just don't hesitate to share it to everyone. But if we are trying to build everything more globally, I think first would be, okay, for sure, we share every knowledge. And secondly, if you still using robot, we can looking forward to apply this existing technology to integrate to these custom robot, which is kind of lower down the level before it's just a fully industry. I hope it's gonna have answered your question.
Actually, that's a very good answer. I can make an example by this artist Olafur Eliasson. He designed a building, and this building is in Denmark, and it is interesting to know that actually there are a lot of molds robotically produced in that building, but you won't recognize that actually there is a very high-end sort of technology used behind that building, because it's exactly what you're saying. Maybe that technology that now we're developing, it's not ready enough in terms of scaling. So that's why I think when it comes to studio teaching and sort of speculating architecturally about these technologies, it's really important also to invest time and energy on that. And I wonder, how can we be more efficient in that front? That's my question with regards to speculation, which somehow you also answered.
Asina, I wanted to add to your question real quick and to build on Neil's, I guess, experience. You know, I'm thinking about, you know, all these scientists coming together at CERN, right? They have a shared history, a shared knowledge, a shared mathematics, and they're tackling kind of the origins of the universe. What is the architectural proposition that equals the CERN question? Because we have an existential crisis of climate change. So that to me is an existential threat that architects should come together as one. So I guess what I'm building on is saying, great work. You guys are future leaders of the field. Now what?
I think this is the dilemma from the beginning of the history. The point that you are mentioning and the point G just mentioned, the point of, sharing the secrets. We have this problem of sharing the secrets since the beginning of history. We have pyramids and the pharaonic civilizations, and we don't have the secrets yet. So we are starting from the beginning.
Yes, but it's not only about a secret or a black box. I mean, I want to ask you, when for example, you design your own machine for a specific design, for a specific project. So in this way, I agree with Sina in terms that this is a lot of, I mean, it's time consuming and energy consuming, because you have to develop your own tool. So you are designing the tool, and this takes you a lot of time. So in a way, it's not only the question about the community, how the community can understand this or how the community can use this. It's also the question about how do you, for example, for students or for architects, for people who understand what you are doing. But anyway, it takes them a lot of time and expertise to develop these tools. That's the question. So when is the time for the design or to study, I don't know, to add others, other fields, I don't know, geometry studies or material studies or light studies, or this affection that we talk about the perception of what you're doing. I mean, this is a lot of, it's too much complexity, because it takes you so time to develop your tool that when are you going to add all these other things that are important in an artistic design as well?
Yeah, Marina, one thing that is very clear what you said is that maybe thinking about these boundaries or subjects might be too limiting, because I think each presenter today basically spoke about a new way of thinking and a new understanding of how they see the future. And I'm very humbled by what I've seen. But anyway, if you can, anyone continue answering Marina's question.
I can sort of kind of carry on the question. Yeah. So actually, my background is I holding my bachelor is architect. So I'm learning from just like sharing community, and you just download the tool and you use it. So looking back at our history, we actually building like only everything prior. We just, okay, you have your security about design the angle, but once you share to the community, and you can just download and you just modify it a bit, and you can learn from it. So the school now we always see like it will be fully academic, and we need to be more, and we need to attend as a physical person. But now we have more, because after pandemic, we actually see how we transfer our information through like social media or share the library, we just download the object. So, and I believe that everyone could get really like access any like to learn how to make a robot just through maybe just, for example, using Arduino. And if you want to go higher, you just learning from the C++ or C# whatever. And for like, okay, so but back to the question is, as an architect, what we are going to do? So you know how to build your object from your tools, and your tool can kind of determine your design. And that I think that will help us to lead kind of another question is like, okay, what is the beauty of this tool after they made this artifact? So we should think about how we train the student from the very ordinary practice to think about how using tool or using the digital knowledge to determine our design, be more specific, or either be more sustainable, or either think about more fit to the local context. So everything we saw, we just based on, from my understanding, share the knowledge and using the tool, and it help you to determine your new design. So we don't see, okay, I'm kind of making the new robot from nowhere. I'm actually I borrowed the knowledge from the Stuttgart, or also combine the different knowledge to somewhere. So always also integrating I think the new is a way to make the new design, or making or shaping the new future. I hope like I didn't find like different word in the sentence.
The balance is the answer, because if finally you take too much time to design the tool and you don't pay attention to the other, it's like you're losing like a lot of things. And in the same time, if you use all the time. Just that's the problem why people who is more creative is a little bit against the develop of these new tools or robotics or other new approaches to architecture, because they feel that it takes them too much time, and they just want to jump to the result. They just want to do something, you know, and we have to balance between these two things, not to think about different fields. Like you have like scientist field and you have architectural field, and then you have like engineer field, because we are in between all these already defining the boundaries. Yeah.
Sorry. Yeah, just in terms of different fields, I was just going to pick up on that, and actually also something that Gustavo was saying earlier on about architecture versus engineering. I don't necessarily see the difference between the two. I know some people say that's architecture, that's engineering. To my mind, it's all kind of in a sense building in some ways. But from working with Baroque, I just want to say something that you know, I think that the strength of architects is that we have this incredible visual imagination. Absolutely. That is also the weakness. In other words, we fetishize the visual in a way that often can hold us back. I often think about the kind of things that we produce, let's say, you know, using processing to produce these kind of complex forms. Actually, they're kind of straightforward in many ways. They're simply the result of a processing script. And actually, the forms themselves, if you take a soap bubble, you know, actually that is incredibly complex. The morphogenetic properties in generating a soap bubble, the internal, external pressure, the surface tension, and so on. I don't think there's any computational tool yet that can actually really model that precisely. But we focus on simply the complex visual forms and think we're being clever and complex. We're not, you know. And I think there's a danger that often you find in some conferences that if it's a sexy form, it gets accepted. If it's not so sexy, it doesn't necessarily get there. Actually, Baroque, just to go back to Baroque again, he actually, I don't know if you've seen these terrible illustrations that he has on his website. No, I mean, he deliberately makes them ugly, you know, so that it doesn't kind of like, you don't get caught up by the sexiness of the form. I think the answer's somewhere in between, but I think as architects, we've got to sort of try and get beyond that kind of the limitation of just operating in a visual way. And I think that structural logics have to be embedded in the way we operate. When I was a student in Cambridge, there was a school of architecture and a school of engineering behind it. There was absolutely no discussion going on. But one of the great contributions that people like Manuel Delander have done is to say that actually the world of science and technology is itself incredibly interesting and can be theorized in a certain way. And just going back to the Digital Tectonics Conference way back when, 2003 or something, Manuel Delander was there with Cecil Baumann and a bunch of other engineers, and he called them material philosophers. And I think we need, as architects, got to see that actually there is something incredibly interesting in structural engineering. It might not be sexy in terms of its form, but actually some of the ideas, the information in it is incredibly rich. So I would want to break down that boundary between the two disciplines.
Before we move on, I think Sina behind the scenes inspired me to do this, but do each one of you panelists want to ask each other any questions? Because this is a very special moment for, I think, all of us here in our viewership. Like, what do you think are challenges, or what do you want to say to each other?
I would like to start and also answer to the last question really quickly. I believe that with the digital fabrication method we have today as architects, we can get to a shift in the paradigm of the architect and the master builder as we were in the ancient times. Because in my research, at least, I'm working with the structural engineer, I'm working with a mechanical engineer, a material engineer, and we are working in the same round table together. And I feel I'm, as the architect, I'm the integrator between all of them, because the material that we are using was under development for almost 10 years, and nobody thought about using it with this methodology that we are using today. And so if I wanted to say if we are doing science or art, I believe today it's more science than art. But the artistic way of thinking about it is really interesting for me, because we have, as Neil said, we have the imagination and the fetish to do anything we want, and until somebody stopped us. So I believe it was really interesting for me to see all of your work, Samin especially, because we are doing something almost the same. And I don't have a question for anybody. I just want to respond. Sorry.
If I want to add something on that, is like, I mean, for me, it's really interesting that how we are positioning ourselves. Are we engineers, as Mariana questioned that? Are we engineers, architects, artists, scientists, or whatever in between? We are something in between at the end. But for me, it's also interesting if we are looking at how the scientists in the other fields, like in physics, in mathematics, in psychology, and different fields and disciplines are defining themselves, is that the scientist is going super deep in some technology and then bring it's as simple as possible in the hand that every single 4-year-old child can also understand it. And I think that what we are doing it, or how we are doing it in this overlap between the different fields, is to bringing up the different knowledges and to mix them out, and or to bring in that as a design. And then I think that's what I really like about the Sina's idea, is that how we are speculating it as a design and bringing it on the top to making it more accessible for everyone else. So maybe sometimes the other people need our black boxes here behind, or maybe sometimes their needs are design visions on top of what we have digged through the technology. And I'm not sure how far we can make everything accessible, but to sharing all of them is amazing. And I think what I really love about this conference event, Digital Futures, I don't know how you're calling it, is that it's super accessible. We don't need to pay 700 euros to go for a fancy dinner of the conference, and every audience need to pay something 100 euros to get on top. It's free for everyone to get in. It's free to have this discussion. And I think that this event has got a huge step, and congratulations to all of you for making it more accessible.
Just to say thank you. Our aim is to make it even more accessible. So, I mean, I just want to say that to my mind, it's fantastic that we literally have Ahmed in Egypt. And we've got, we've got an Iranian, we've got an Israeli, we've got everyone all together. It's a fantastic thing. But the challenge is, how do we disseminate this information and make it available? Because I personally think, I mean, actually, I had a comment from Philippe Morel a few days ago. He said, you guys, you don't know what a contribution you're making. From France, in the situation in France, most university professors are complete dinosaurs. And this is such an interesting teaching resource. And our challenge is, how do we make this accessible? Because I think today, I found out more today from any lecture I've been to, actually, must say, from the different sort of probes that you guys are all making. And there's a kind of form of collective knowledge coming together. And it's really a question of how we can find a platform to share that knowledge, rather than all operating in our own individual ways, and to make these bridges. So that's the challenge, and that's what we're trying to get towards. I mean, I would just simply say that my motivation has been, I used to teach where Sina teachers in Dessau, when everyone went with, they had no money. No one had any money. They couldn't afford to go to the top schools. And part of this is about an attempt to democratize things in many sort of ways. And education shouldn't be a privilege. It should be accessible to everybody. So that's what we're trying to do. That's what we're trying to do. It shouldn't be based on whether you can pay the fees to go to the AA or Columbia or whatever. So, but I mean, maybe collectively in the future, we can build upon this and find a way to network and share the knowledge and make it even more accessible. But this was a fantastic session. So I just want to thank everybody. Amazing, amazing.
We had a reflection, yes.
Okay, thank you. Actually, my background is in technology philosophy, and my question is that how you, as a leading expert in your field, to perceive the future of architecture with the robotics fabrication technologies, Because as we see that now with the algorithms and the advanced technologies, it seems that the interactions between the buildings, the materials and humans have become more dynamic say directly. Previously, the soil or the wood or the bricks are just a kind of object, very purely object. And now currently, we can reorganize those materials. The bricks, we can use different amazing and unbelievable previously structures, shape, and curves. So I'm saying that what if we can say that architecture is becoming more organic? And what do you think about how the technologies will shape architecture? Maybe in the future, in the long term, but it's just an open question. So I don't think it is.
I think that's what they've been, in their own particular ways, everybody's been exploring today. It's a kind of, it's a huge question, yeah.
Yeah, I would like to, my point is, I would like to know how the general public can answer your question, I believe every architect may have his own vision, but I'm still stuck at that point, how the general public can see what you are doing, what about their perception, their needs. Yes, they used to use this kind of materials, affordable materials like brick and mud, sand, and so on, wood, trees, tree trunk, building their own primitive architectural forms. But with these kind of technologies, how they would contribute using these technologies and these available materials, what possibilities, what digital future possibilities we may have in the future, I don't know. I believe the answer from the general public side would be very different from our side. This is what I believe.
Just to build on Ahmed's point, I think that my question, we can maybe think about it in two ways. Ahmed, we want to know what's happening now locally in our time, but each presenter is really doing a long-term proposition to basically poke a hole into the future and deflect how our society is going to react to what's going to happen to us. So, but I would love to hear your thoughts as presenters about what's currently happening now and the future.
I have a question kind of following up on all of this. I was just looking at your GitHub, and this may seem very practical, but not all that many architects in this whole range of universities and everything where we're working actually are documenting a work and sharing it that directly, right? And I'm curious if you could offer any perspective on how successful you think it is to share code and software and designs through these kind of more typical platforms used in software engineering like GitHub, and just your perspective on that.
I think it's quite useful because so back to like if I'm still a student, then I don't know. Actually, I've learned how to code in the Swift language just through the YouTube or any like online course. That I think that would be really useful. Everyone share the part of the script and also document and would make it a small tutorial. So we are not limiting ourselves be only teach in academic or into become a position that you can teach or hold in the studio. Everyone can be the tutor, everyone can be the teacher. So sharing knowledge is actually helping or providing for the people who do not access these things. So I think it's really important to just documenting is pretty important. And also I want to answer the part of the question from Jen is, I think you have mentioned a really important question. If we are kind of this project I see today is related to the brick or concrete or printing, and we are actually now we can use our technology to observe what the primitive building, what the primitive builder what the secret inside how we dealing with the heterogeneous material become more, well, actually we're using a robot, we're using any sort of a technology to duplicate or to make the same capacity, or making our homogeneous material to more heterogeneous. So it become to nature, become a natural beauty. And I think in the end, our building, our architecture should be more like, okay, there's no straight line. Then could be more like our grandfather, or you were from someone from ancestor. The building like the really nature.
Yes. Yeah. Unfortunate, we run out of time. I believe we need, more days, few days. I think this discussion should extend to like 2 weeks. It's very exciting. For the most important from my point of view, that you believe that you cannot change the world for a better place. So please believe in yourself. On behalf of Digital Futures, I would like to invite our audience to submit and contribute through our open calls, the next calls. Our discussion today was very amazing and exciting. But as I mentioned, I would like to extend for weeks, but unfortunately we run out of time. So we will be waiting for your questions and discussions on our Discord channel. Thanks for everyone for joining us today. That discussion was very, very, very exciting. Especially myself, I'm so excited. I hope we can have future discussions on some of these topics. We have next week a presentation on digital fabrication, the third presentation on digital fabrication. And after that will be something very interesting. Wait for us. We'll be waiting for you. See you next week on the same time, every Saturday. Thanks for everyone. Bye.